Could Earth be inferior for supporting life? Research teams publishing their findings in the astrophysical journal present compelling evidence for this controversial claim. Through comprehensive analysis of information gathered by NASA's Kepler Space Observatory, research teams examined over 2,000 exoplanets located within zones considered potentially suitable for life around their host stars. The most remarkable discovery reveals that more than 120 of these distant worlds classify as gas giants, with each potentially hosting multiple natural satellites. Evidence suggests these locations offer our greatest probability of discovering life beyond Earth. These orbital bodies would presumably contain liquid water reserves, while their massive planetary hosts serve as protective shields against harmful cosmic radiation, generating magnetic field barriers and atmospheric protection systems. Put simply, all the favorable conditions Earth acquired through extraordinary circumstances and cosmic fortune come naturally and freely to the moons of these giant worlds. Yet a significant complication exists. Despite extensive astronomical research efforts and detailed observations conducted using the James Webb Space Telescope, no confirmed exomoon detection has occurred to date. In contrast, within our own solar neighborhood, gas giant planets possess a total of 131 known satellites. Numerous researchers theorize that multiple candidates among these moons could support not merely Earth-type biological systems, but serve as optimal destinations for human settlement. We'll examine this systematically. Which natural satellites might support more than simple bacterial organisms? What agricultural possibilities could future space farmers pursue in these environments? And what makes a frigid, shadowy world orbiting Saturn superior for human colonization compared to Mars? Additionally, what forms might biological systems take on the moons surrounding gas giant planets in our solar system? Historical misunderstandings regarding natural satellites. Throughout decades of astronomical study, researchers maintained that every satellite in our solar system resembled Earth's moon, essentially barren, geologically inactive rocky bodies. Yet multiple discoveries during subsequent investigations fundamentally challenged these assumptions. During the early 1970s decade, Pioneer 10 and Pioneer 11 spacecraft conducted humanity's initial close-range examinations of Jupiter's moon Io. Transmitted data exposed an unexpected anomaly. The small satellite's measured mass exceeded theoretical predictions. Typically, such diminutive celestial objects comprise water ice, mixed with silicate materials. However, Io demonstrated significant concentrations of silicate rock formations and metallic iron, establishing its position as the solar system's most density-concentrated moon. Scientists focused primarily on Io's tenuous atmospheric characteristics. Yet, comprehensive satellite analysis faced obstacles from surrounding radiation zones that caused equipment damage to Pioneer instruments. Fortunately, the 1979 Voyager mission expeditions resolved these limitations. Their superior technological equipment successfully captured detailed, high-resolution surface imagery of Io. Research teams expressed astonishment at their observations. The satellite displayed complete crater absence, contrasting sharply with other astronomical bodies. Initially, scientists theorized that Jupiter's gravitational influence simply attracted all incoming meteorites. However, researchers soon identified geyser formations in Io's photographs, clearly indicating active volcanic processes. Investigation revealed that Jupiter's gravitational forces, combined with tidal influences from neighboring satellites, continuously stretch and compress Io's internal structure, generating substantial heat. This process produces molten silicate magma containing elevated sulfur concentrations, which erupts across the surface. Distinctive yellow sulfur deposits blanket existing craters and the moon's entire exterior. When combined with radiation exposure, these conditions create lethal environments for any biological systems. Nevertheless, beneath Io's surface layers, relatively protected zones exist. As magma penetrates surface areas and subsequently cools, it forms geological structures known as lava tubes, where water preservation occurs and microorganisms might potentially survive. Earth hosts sulfate-reducing bacterial species that process sulfur-based compounds and utilize pure sulfur elements during metabolic activities. These organisms thrive in groundwater environments with elevated hydrogen sulfide concentrations. Human settlement on Io, obstacles and potential solutions. Should human colonization of Io proceed, settlers would necessarily adopt strategies similar to sulfur processing bacteria, establishing underground habitation systems positioned away from volcanic activity zones. Without such precautions, extremely high probability exists that all colonial structures, including their human inhabitants, would face destruction from volcanic eruptions within several years. Subterranean-based construction could substantially minimize exposure to dangerous radiation levels. However, regardless of protective measures implemented, complete radiation shielding remains impossible. Furthermore, even heavily shielded electronic systems would eventually malfunction, paralleling the pioneer equipment failures. Does our solar system contain locations sharing Io's characteristics while avoiding such extreme, hazardous radiation levels? Triton, Neptune's distinctive natural satellite. Triton represents another moon exhibiting volcanic characteristics. Accurate information regarding this celestial body first became available in 1979 during Voyager 2's flyby encounter. Scientific teams anticipated observing a geologically inactive rock completely lacking dynamic processes. Instead, returned imagery revealed intricate topographical features across the satellite. Furthermore, massive geysers reaching 4-mile heights launch material directly into space from various surface locations. These phenomena occur at temperatures reaching -235 degrees Fahrenheit. Such observations confirm cryovolcanic activity. Under these extreme conditions, ordinary water exhibits behavior identical to molten lava. Only bacterial spores maintaining dormant states could survive on Triton's surface while awaiting improved environmental conditions. Regarding subsurface water reservoir systems, current knowledge remains insufficient for drawing definitive conclusions. Therefore, should base construction on Triton ever occur, reliable thermal insulation systems would require development, rather than radiation protection measures. Local resource utilization could achieve this, specifically, large ice flocks of various compositions. These formations could provide water extraction capabilities, while fuel resources literally exist beneath surface levels and could facilitate ice melting processes. Triton contains oxygen and hydrogen reserves. Contemporary technology could synthesize rocket propellant from these materials. However, the primary colonization barrier involves extreme distance. Neptune's moon orbits 30 times farther from the Sun than Earth, requiring journey durations of at least 12 years under the most favorable scenarios. Current technological capabilities cannot transport essential cargo loads of materials and food supplies necessary for colonist survival across such vast distances. NASA's planned research mission to Triton faces indefinite postponement. Jupiter's captivating moon system. Practical considerations suggest focusing on satellites orbiting nearby gas giant planets. Beyond Io, Voyager missions identified additional Jupiter moons of significant interest to astrobiological researchers. The Galileo spacecraft reached Jupiter in 1995, transmitting over 30 gigabytes of unprecedented data back to Earth. Europa attracted particular scientific attention because Voyager had documented crack formations across its ice-covered surface. Galileo confirmed these linear features undergo constant changes. This indicates they represent fractures in ice layers covering an underlying liquid water ocean. Contemporary scientific understanding suggests Europa's ocean volume equals 2 to 3 times the combined capacity of all Earth's oceans. However, precise water composition remains undetermined. Sample acquisition would require not only successful landing on Europa's surface, but also drilling operations through ice layers to depths of 15 to 20 kilometers. Nevertheless, simpler sampling methods exist. Hubble Space Telescope observations indicate Europa's ocean may erupt directly into space without reaching surface levels. When water forms these towering fountains, passing spacecraft could potentially capture and collect water specimens. Sample analysis would illuminate ocean composition while answering the fundamental question: does life exist beneath Europa's ice cover? Biological possibilities on Europa. Astrobiological researchers theorize these could include organisms resembling Earth's single-cellular life forms capable of surviving extreme environmental conditions, including those inhabiting the Mariana Trench. Elevated pressure, complete darkness, and frigid temperatures don't prevent their survival and reproductive processes. Most probably, these would resemble bacteria similar to Pyrococcus denitrificans. These bacterial organisms exhibit remarkable environmental adaptability. They survive in oxygen-abundant environments and completely oxygen-free conditions. Their nutrition depends on nitrogen and sulfur substrates while tolerating pressures 200 times greater than atmospheric levels. Under laboratory conditions, they maintained growth under pressures 4,000 times normal levels. This equals nuclear explosion pressure equivalents. Unfortunately, human physiological resilience falls far short of such capabilities. Europa colonization, technical engineering obstacles. Human colonization of Europa would require NASA engineering teams to consider expanded approaches. Underwater city concepts beneath ice layers likely seem appealing. However, determining project feasibility requires initial ice drilling operations and deploying robotic exploration systems. NASA currently develops vertical drone technology designed to float on water surfaces. This capability would function similarly to enclosed balloon systems. Additional requirements include wheel installations enabling travel throughout the satellite's interior regions. Should environmental conditions prove favorable, subsequent phases would involve underwater base construction for direct oxygen extraction from water sources. In practical terms, living beneath Europa's ice represents not merely one option, it becomes essential necessity, because the satellite's surface experiences extreme radioactive conditions. A single day on Europa would expose colonists to radiation doses nearly 1,800 times exceeding annual Earth radiation levels. Such exposure would prove lethal to all living organisms within 1 month. Therefore, if underwater-based systems prove impractical, whether ice shell thickness exceeds manageable limits, or water toxicity presents problems, Europa colonization concepts would require abandonment in favor of seriously considering alternative Jupiter moons. Ganymede, a more secure option. Ganymede stands as the solar system's only satellite where surface radiation presents minimal threats. Credit belongs to its magnetosphere, discovered through Galileo orbiter observations. Typically, such powerful magnetic field systems exist exclusively around planets, not natural satellites. Yet Ganymede exceeds Mercury's dimensions. Essentially, it constitutes a complete planet orbiting Jupiter. Additionally, Galileo detected subsurface ocean systems on Ganymede. This appears characteristic of gas giant satellite systems. Such ocean formations may total 4 separate bodies. Scientists theorize they contain more water than all planetary systems combined, if accurate, with ice layer separations. These formations most likely developed under varying conditions, suggesting each could support distinct biological forms. Within saltwater environments, not only bacterial life could exist, but larger organisms as well. For instance, radiolarians, microscopic plankton containing internal mineral frameworks composed of silica or strontium materials. Their sizes don't exceed millimeter measurements. However, saltwater environments could support organisms tens of times larger. Artemia, small crustacean species inhabiting saltwater environments worldwide. They reproduce without mating partners. Typically, they produce eggs, though extreme conditions trigger live birth adaptations. Artemia eggs maintain viability for extended periods without saltwater environments. Should Ganymede host Earth-type crustacean species, they could provide nutrition for future colonists. Crustacean-based paste provides such concentrated nutrition it could substitute for meat products, while requiring significantly less energy than laboratory-grown meat production. This factor, combined with radiation protection, establishes Ganymede as quite promising for colonization purposes. Ganymede's atmospheric characteristics. Moreover, an additional essential life-supporting condition exists. Initial Earth-based telescopic observations detected thin atmospheric layers surrounding Ganymede, though Voyager failed to confirm these findings. However, 1999's spectral analysis enabled scientists to definitively establish that Ganymede possesses an oxygen-containing atmosphere. Naturally, atmospheric density remains insufficient for breathing or heat retention. Consequently, Ganymede's surface temperatures reach -300 to 400 degrees Fahrenheit. Nevertheless, even minimal atmospheric layers around satellites represent extremely rare phenomena. Oxygen can be collected, processed, and concentrated for colonist respiratory needs. However, whether considering Io, Europa, or Ganymede, only limited isolated locations exist where primitive extraterrestrial life could thrive. Humans would require enormous efforts compensating for atmospheric absence, radiation contamination, and additional complications. Titan, the most favorable world. Yet within our solar system, one location exists where such complex solutions become unnecessary. This absolutely unique celestial body orbits Saturn. This dark and frigid world may prove the optimal location for life throughout the solar system. During flyby operations, Voyager spacecraft couldn't photograph the satellite's surface because thick cloud formations obscured visibility. Penetrating these layers required specialized mission planning. On January 14, 2005, the Huygens probe achieved successful landing on Saturn's largest satellite, Titan. Through cloud penetration, the probe observed something extraordinary, a feature no other planetary satellite in our solar system possesses: dense atmospheric layers. Furthermore, similar to Earth, atmospheric composition consists primarily of nitrogen while providing effective protection against lethal cosmic radiation. However, similarities conclude there. The Moon's surface remains invisible from space due to hydrocarbon smog development in upper atmospheric regions under diminished solar illumination. This prevents light penetration, creating perpetual twilight conditions across Titan's surface. Nevertheless, according to Huygens data, Titan's atmosphere demonstrates high activity levels. Wind systems similar to Earth's trade winds exist. Daily, they transport warm air currents from equatorial regions toward polar areas. Consequently, Titan's equatorial zones develop dune formations resembling Earth's desert systems. However, the particulate matter consists not of silicate materials, but hydrocarbon granules resembling breadcrumb textures. Rather than stone formations, Titan's landscape comprises ice fragments. At -290 degrees Fahrenheit, they achieve rock-like hardness. However, similar to other gas giant satellites, Titan contains liquid water. These reserves exist in subsurface ocean systems approximately 50 miles below surface levels. Resilient bacterial organisms similar to Earth species could thrive excellently in such environments. However, this doesn't represent the sole hypothesis regarding extraterrestrial life on Titan. Unusual life forms on Titan's surface. Ethane and methane rivers and seas flow across Titan's surface. On Earth, these substances exist in gaseous states, but under such frigid conditions, they maintain liquid phases. Astrobiological researchers believe these extraordinary water bodies could generate life forms completely unlike terrestrial organisms. During 2020, the Astronomical Journal published research describing atmospheric molecule discovery on Titan, a carbon-based compound designated cyclopropanolidine. This proves quite unusual because carbon-based life primarily utilizes this molecule within interstellar dust cloud environments, and within Titan's atmosphere, cyclopropanolidine should undergo decomposition. What process could continuously generate this compound in quantities visible from Earth? Extraterrestrial biological systems could represent a viable explanation. Similar molecules undergo constant production and consumption by living organisms, establishing them as biological indicators. However, Titan-based life would require water substitutes for cellular metabolic processes. Most remarkably, astrobiological researchers have successfully modeled membrane systems capable of processing liquid ethane and methane. These membrane structures comprise nitrogen, carbon, and hydrogen molecular components. They could serve as foundations for genuinely unusual cryogenic biological systems. Analogues of terrestrial ice worms inhabiting North American glacier systems could currently traverse Titan's dune formations. Furthermore, within low-gravity satellite environments, they could achieve substantially larger dimensions. However, transportation via these organisms, as depicted in fictional films, remains unlikely. Upcoming Titan missions. Shortly, we may receive information regarding Titan life forms. NASA plans launching the Dragonfly mission to the satellite in 2028. This represents more than standard probe technology. It constitutes a quadcopter system capable of aerial surveillance across the satellite's surface while searching for anomalous phenomena. Research shouldn't limit itself to distant observation. Planning should begin for future expeditions with more ambitious objectives, regardless of whether this mission discovers life on Titan. Titan's superiority over Mars for human settlement. Despite appearing inhospitable and frigid, Titan represents the most promising colonization destination throughout the entire solar system. This comparison includes Mars, which Titan surpasses across multiple critical parameters. Initially, colonists from any cultural background will require abundant construction materials. Mars-based construction plans involve utilizing soil and rock materials to maximize available capabilities. Meanwhile, Titan provides unlimited supplies of liquid and solid hydrocarbon resources from which polymer synthesis becomes easily achievable with unlimited shape possibilities. Unlike Mars's rigid rock formations, these flexible materials enable construction of residential quarters, laboratory facilities, and greenhouse structures. Furthermore, future excess hydrocarbon production could be transported to Earth. Considering long-term habitation requirements, food and water availability becomes equally crucial. Successful cultivation of edible plant species on Mars would require Earth soil imports and dependence on fragile, closed-loop regeneration systems. Conversely, Titan's atmosphere already contains sufficient nitrogen plus ammonia compounds. This enables plant cultivation within specialized greenhouse environments and even self-sustaining ecosystem development with minimal risk factors. Primary challenges would involve temperature management. Mars contains limited water supplies, primarily existing as polar ice formations. Therefore, transportation across great distances becomes necessary. On Titan, water erupts directly onto surface areas. Despite containing approximately 10% ammonia functioning as antifreeze, purification processes remain straightforward. Hydrocarbon river systems would provide substantial colonist assistance, enabling electrical power generation. Furthermore, accidental electrical sparks near massive liquid fuel quantities wouldn't present concerns because Titan's atmosphere lacks oxygen, making ignition physically impossible. Mars energy production depends exclusively on solar panel systems requiring constant cleaning following dust storm events. These maintenance operations would require bulky protective suit systems because Mars's atmosphere consists primarily of toxic carbon dioxide with extremely low density. Mars' atmospheric pressure equals only 0.6% of Earth levels. Conversely, Titan's atmospheric pressure exceeds Earth levels by 50%. Therefore, only cold weather protection suits and respiratory equipment would be required. Large oxygen quantities could be extracted from satellite subsurface water sources. However, breathing apparatus systems would require extreme reliability, preventing leakage incidents. Titan's underground ocean could be populated with cyanobacteria colonies. Powerful ultraviolet lighting installations could facilitate sufficient oxygen synthesis by these microorganisms. All these operations could be conducted from base facilities resembling existing Martian settlement designs. The sole difference involves thermal insulation requirements rather than pressure compensation and deadly radiation protection systems. This necessity exists for colonist comfort and because human inhabitants and their equipment would generate substantial heat quantities on Titan. Without thermal insulation systems, bases and colonists would literally melt through hydrocarbon soil layers and sink downward. Transportation and movement on Titan. Furthermore, the most natural Titan transportation methods involve flight and aquatic travel. NASA currently develops specialized hydroplane designs capable of aerial travel through dense nitrogen-methane atmospheric conditions while gliding across satellite lake systems. Most remarkably, Titan enables human flight without specialized apparatus. This represents an ideal location for realizing humanity's ancient flight aspirations. Aerial movement could be achieved simply through our movements. Gravitational forces here equal only 14% of Earth levels. Therefore, foldable wing systems could transform any colonist into a bird-like entity. Long-term benefits compared to Mars. Nevertheless, despite these advantages, Mars maintains superiority regarding accessibility factors. Red planet journeys require less than 1 year, while Saturn orbital travel demands 7 years. However, ensuring solar system survival makes this a manageable concern. Both Earth and Mars will become unsuitable for extended habitation in future timeframes. Within 1 billion years, the Sun will generate 10% additional heat output, rendering Earth uninhabitable. Ocean water will begin boiling and evaporating. Accumulated water vapor will enhance greenhouse effects, transforming our planet into a hellish furnace resembling Venus within several thousand years. Within 4 billion years, the Sun will transform into a red giant star, consuming nearly all nearby planetary bodies. Should Mars survive, it will become the closest solar world, resembling current Mercury conditions, an extremely hot, molten rock formation. Colonial settlements located there would simply melt. However, following such inter-solar system catastrophe, gas giant satellites will warm considerably and become substantially more comfortable for subsequent tens of millions of years. Final considerations: select your future residence. Therefore, decide now. Which satellite would you choose for humanity's future survival? Thank you for watching this video. If you liked it, give it a like and don't forget to subscribe to the channel. Thank you and see you in the next videos. Take care.